Welcome back to the deep dive. So if you've ever had to optimize, say, a chemical or a biological process, you probably know this already. The biggest gains, i- they aren't really found in the ingredients themselves. It's all about the timing and, well, the control of how you add them. Today, we are deep diving into the engine room of modern biotech, microbial bioprocessing. And this isn't just about growing bugs for product. It's about a really sophisticated, radical shift in industrial control.
That's absolutely right. Our sources give us a fantastic roadmap for this. They really show the transition that's happening across industries. We're moving the fundamental production platform from, what you could call the traditional batch model.
Right, like following a recipe.
Exactly. Think of it as a precise but finite kitchen recipe.
Okay.
We're moving from that to a sustained, uninterrupted production flow. And that second model is, well, it's less like a kitchen and much more like an endlessly running, optimized assembly line.
So the mission for this deep dive is to really understand that fundamental shift in control. The traditional approach,
Yeah.
fed batch, is still dominant. It's flexible. People get it. But it is inherently episodic.
Mm.
You start a tank, run for 7 days, you harvest, then you're down for maybe 24 hours cleaning and sterilizing before you can even start the next one.
And the continuous approach aims to just eliminate that downtime completely. You're shooting for uninterrupted production and, of course, superior equipment utilization. What's truly fascinating, and what the sources really highlight, is that this is fundamentally a change in how we think about control. We're moving away from these fixed, predetermined recipes. Instead, we're treating feeding and dilution as time-varying decision variables.
Okay, so you're turning what was a simple schedule into a highly complex, dynamic optimization problem that has to be solved in real time.
That's it, exactly.
Let's unpack that then. This core philosophical difference. If fed batch is a recipe and continuous is real-time adjustment, how does that change the primary variable we're trying to control?
Well, in fed batch, your primary design variable, it's really time. You're designing a nutrient feed profile,
Yeah.
right? A kind of trajectory. And that trajectory's job is to shepherd the culture through a very specific, predefined sequence of physiological states.
All within a finite campaign.
All within a finite campaign. You're just focused on getting from start to finish successfully before you hit a physical constraint like volume or oxygen capacity.
So the nutrient profile is basically a trajectory shaping control input. It guides
Yeah.
the culture. But continuous systems, they completely flip that.
They do. In continuous systems, the objective isn't managing a finite path. It's establishing and sustaining steady or quasi-steady regimes that deliver constant productivity, theoretically indefinitely.
Wow.
So when we look at control in that context, the process flows. So the dilution rate, perfusion rate, cell bleed, those become the dominant levers you pull. They're the variables you manipulate to tell the cells exactly how fast to grow and what metabolism to run.
I see. So instead of just timing a nutrient addition, you're controlling the flow rate of the entire system to maintain a desired state. And that shift in control structure, that must be why it pairs so well with advanced tools like model predictive control.
Absolutely. That structure is just ripe for advanced control. But the sources provide this really crucial unifying perspective we need to remember. Despite the operational differences, batch, fed batch, and continuous, they aren't fundamentally different platforms. They're just extensions of the same underlying logic.
And that logic is?
Shaping metabolism through controlled fluxes, a controlled flow of materials, all while operating under these strict physical, biological, and economic constraints. The decision to run batch versus continuous, at the end of the day, is a constraint problem.
So if that's the theory, we have to start with the foundational tools to understand how this all works. What did the pioneers develop?
We have to begin with the canonical model.
Yeah.
It's chemostat. It's the simplest expression of continuous culture, and it's arguably the most important experimental tool in all of microbiology.
Okay, describe the setup for someone who, hasn't been in a bioreactor lab for a while.
It's pretty straightforward physically. You have fresh medium with a single growth-limiting substrate, and it's supplied to the reactor at a constant fixed flow rate. At the same time, the culture broth, so cells, products, spent media, is withdrawn at the exact same rate
To keep the volume constant.
to keep the reactor volume perfectly constant. And the key insight is how the biology responds to that fixed flow, the system. It converges to a unique, stable, non-zero, steady state.
And what defines that state?
The specific growth rate of the cells, which we call mu, becomes precisely equal to the dilution rate, D. So if you speed up the flow, the cells literally have to grow faster to avoid being washed out. This gives you a truly growth-controlled steady state with time-invariant concentrations of everything.
It sounds incredibly powerful for research. Incredibly powerful. You can tune the growth rate with extreme precision just by turning a pump.
It is. It's its greatest value. Researchers use the chemostat to systematically investigate how growth rate impacts every single aspect of the cell. Gene expression, metabolic flux, product formation. That kind of quantitative insight is critical because it tells us, for example, when during a fed batch run, we should slow growth to maximize product. The chemostat gives you the data to design those trajectories.
Okay, but here's where it gets really interesting. If it's such a pristine, powerful experimental tool, why hasn't the chemostat completely taken over industry? The limitations must have driven the development of these modern systems.
That's the crux of the industrial adoption problem. Historically, there were three big hurdles. First, just logistics. Continuous systems run for a long time, so contamination risk goes way up. If a batch run gets contaminated, you lose, 5 days?
Right.
If a continuous run gets contaminated on day 30, you lose 30 days of production.
Stakes.
Extremely high. But the second, and maybe more insidious limitation, is genetic drift. Over these long-run times, even a single non-producing cell that has a tiny fitness advantage, say, it doesn't waste energy making your product.
It'll take over.
It'll multiply and outcompete the producing strain. You risk selecting against your own desired organism.
So the very nature of continuous flow, forcing adaptation,
Yeah.
also forces evolution away from your target.
Wow.
A single mutation could ruin months of work.
And that's why strain stability is so important. The third limitation was just, greater operational and regulatory complexity compared to the discrete, well-established batch processes. Industry likes predictability.
So how do we get around those fixed flow limitations? Because the sources show that continuous cultures don't have to operate at a fixed flow.
Yeah.
They could be dynamically adjusted, right,
Right.
using the biological signals themselves.
Exactly. And that takes us to the early feedback-controlled modes, the oxostats and turbidostats. These systems relax that fixed dilution rate assumption completely. Instead of controlling the flow, they control a biological variable. A turbidostat, for instance, regulates optical density. As the cells multiply and the culture gets cloudier, the system automatically increases the dilution rate to keep that cell density constant.
So it's self-regulating to hold a set point. And the turbidostat usually operates the cells right near their maximal growth rate.
Correct, because the flow keeps increasing until they just can't grow any faster. And the pH oxostat it's a wonderfully elegant solution. Instead of using concentrated acid or base for pH control, the system just uses the medium addition itself. If the cells produce acid as they grow, the system detects the pH drop and increases the medium flow to buffer it back up. So the dilution rate is then directly determined by the rate of growth-associated acid production.
That is a great example of biological feedback, adjusting an engineering parameter. These foundational tools really pave the way for the modern hybrid architectures we see now.
Indeed. Advances in cell retention and, better sensors have dramatically renewed infra and continuous processing, often through these hybrid configurations. And the most effective of these are the cell retention systems, like perfusion and retentostats.
How do those differ from a standard chemostat?
Well, a chemostat washes out cells and medium at the same rate. A perfusion system uses a physical cell retention device, like a filter or a centrifuge, to continuously exchange the spent medium for fresh nutrients, but it keeps the vast majority of cells inside the reactor.
And the massive advantage of retaining all those cells is?
You can achieve just incredibly high volumetric cell densities. Instead of, say, 20 grams of cells per liter, you might hit 100 or 150. And you do this while maintaining a very low next-specific growth rate, sometimes barely above maintenance. You've essentially created a permanent, extended production phase. The biomass is held constant, and you are just continuously harvesting product.
And perfusion is the standard in mammalian culture for things like monoclonal antibodies.
It's the established norm there, absolutely. But we are now seeing microbial applications emerging for complex enzymes, biofuels, organic acids, especially where you can integrate it with continuous downstream processing. But of course, these systems bring new challenges. You have to deal with membrane fouling, shear stress from pumps, and you have to meticulously manage a bleed strategy to limit the buildup of non-producers or dead cells.
So you're always fighting that old enemy.
Yeah.
Genetic drift.
Always. Another fascinating hybrid approach that gets around the limits of a single tank is using multiple stages in series.
Multi-stage continuous reactors. Explain that progression.
You're spatially separating the biological functions. See, the optimal conditions for cell growth are often very different from the optimal conditions for cell production. So in a two-stage setup, stage one operates at a high dilution rate to maximize biomass generation, just make cells. Then that culture flows directly into stage two, which operates under completely different conditions, maybe a restrictive nutrient mix, a different pH, specifically tuned to maximize product synthesis.
So it's the physical realization of that analogy from earlier. Stage one builds the factory, and stage two just runs the factory. It's optimizing for output, not growth.
Exactly. And because it's uninterrupted, these systems can get per-volume titers that are comparable to a batch process, but with vastly higher overall productivity. You can even use chains of stirred tanks to essentially approximate the temporal progression of a fed batch process, but it's laid out in space instead of over time.
Okay, this sounds way more complex to build and operate than a single tank, but the economic promise must be huge. The sources cite cost reductions up to approximately 50% in some scenarios, like vaccines and biologics. That kind of number forces manufacturers to really consider the complexity.
It's the ultimate incentive, but for most companies, adoption is staged. They move from simple batch to fed batch, then maybe to an intensified fed batch where they add a partial bleed or something, and only then move to full perfusion or multi-stage. It's an evolutionary path, really. They only make the jump once strain stability is proven.
So we've talked about fed batch as a recipe, continuous as sustained production. But the sources suggest they're converging under this common framework, dynamic optimal control. What does that actually look like for fermentation?
This is where we formalize the entire problem. Optimal operation is defined by mapping out three key elements: the objectives, the decision variables, and the constraints.
Okay, let's start with objectives. It's not just make more product, is it?
No, rarely. It's often about maximizing space-time yield. So, how much product mass you get per reactor volume per total time, or more practically, maximizing net profit, which means balancing product value against the cost of media, cooling, utilities, everything.
And the decision variables are the levers we can pull.
Precisely. These are the things we can adjust dynamically: feed rates, dilution rates, temperature, pH. And then you have the reality of it, the constraints.
Hard limits of the system.
Physical limits, like the max rate you can pump in oxygen. Biological limits, like the maximum growth rate of the organism. And operational limits. And crucially, when you solve this problem mathematically, the answer is rarely a single, static, steady state.
It's not simply always run at 0.1 per hour.
Never. The optimal solution is a time-varying compromise. It involves exploiting high-growth phases at the start to build the biomass factory, followed by a controlled transition to lower growth rates, which favors production while respecting the reactor's physical limits.
And if you apply this kind of rigorous optimization to an old fed batch process, does it justify the common industrial heuristics?
Yes, absolutely. The optimal trajectories derived mathematically. They often just formalize what experienced operators have known for decades. The structure is almost always the same: rapid initial growth, a transition where you slow growth to switch on production, and maybe a final phase to let the last product accumulate. It turns guesswork into verified optimization.
But those offline trajectories are great for design, but real processes have uncertainty. You need to adjust in real time.
And that's the necessity for closed-loop optimal control. The gold standard here is Economic Model Predictive Control, or MPC. It's really the highest level of control sophistication.
How does MTC work here?
Instead of following a fixed recipe, the MPC system, every few minutes, resolves that entire dynamic optimization problem over a moving horizon. It forecasts what's going to happen over the next, say, 12 or 24 hours, based on the current state, and then decides on the best flow rates to use right now to maximize the economic objective.
So if the dissolved oxygen suddenly drops, the MPC doesn't just cut the feed. It instantly calculates, if I slow the feed rate by 15% for the next 2 hours, my total profitability for this batch will be maximized compared to all other options.
That's exactly what it does. It maximizes profit moment to moment while ensuring all constraints, all the safety and physical limits are respected. It's computationally heavy, but it's what's needed. And beyond classical MPC, we are even seeing alternatives emerge, like model-based reinforcement learning, or RL.
RL, like for AI training, how does that fit in?
Well, RL can serve as an adaptive upper-level optimizer. Instead of relying purely on a first principles model of the cells, the RL system learns the optimal control policies by simulating or running the process, getting rewards for profit, and being penalized for bad outcomes. These learning methods are really attractive for long-horizon, nonlinear operations where your biological model might be incomplete.
So, to synthesize this, the industrial world is seeing that the future is continuous, or at least optimally controlled. While fed batch is dominant today, its design is governed by the same optimization principles as these advanced systems. The line is blurring.
And for you, the sources suggest a clear development pathway. First, use the foundational tools, chemostats and oxostats, to really characterize the core biology, the growth rate dependent fluxes. Second, use that data to apply dynamic optimization, or MPC, to design robust fed batch trajectories.
And finally, adopt the continuous element cell retention multi-stage reactors incrementally. Only introduce that complexity where the economic case is clear and measurable. It's a pragmatic evolution.
It's about being smart with your control structure to capture the intensity of continuous flow while maintaining the robustness that comes from deep process understanding.
Since the objective in optimal control is so rarely a single static state, but rather a time-varying compromise, a continuous search for the sweet spot that balances growth with production, how might this philosophy of time-varying compromise apply to optimizing non-biological long-term industrial processes in your own field where constraints are constantly shifting? That's something to think about long after this deep dive ends. Thank you for tuning in.